I guess we're going to start pretty low because I noticed that a lot of you are, not systems people and not Linux people even. So I think that we should probably start off with some of the basics of, are you all well aware of things like data structures and whatnot, or do we need to start there? Okay. All right. So since you all know that data structures exist, I don't know which ones are used in the kernel, but because I don't do it. But I do know that someone here should know. Anyway, so I'm going to kind of try to get an idea of where we should go with this, though, because without having kind of a direction, it's really kind of meaningless. So if you've never kind of done systems level stuff, I think it's important to kind of start at the lowest level where you're talking about things that exist on every system. So I think we need to talk about things like main.c, where things actually start booting from, and even some of the very basic algorithms, how the scheduler kind of works. Not a deep discussion of, how the scheduler works technically, because there have been at least 3 different implementations and as many kernels. But I think it's more important just to know what parts of an OS there are, how Linux kind of structures itself compared to other OSs, and if anyone has anything to add, I'd really like it if you'd speak up. I don't think that we have a mic that we can pass around right now, so if you wouldn't mind, it would be really cool if, I don't think that's working, never mind. So you can come up here and I'll hold this thing up to your face. What's up?
I think one thing you could do is you could ask people what they'd especially like to see. I'd be interested in seeing the boot process,
right?
How that all works, memory management, virtual memory,
right?
device drivers. Just a list of things that we could do.
Well, that's kind of where I was getting. So we will kind of, take suggestions from you guys. I kind of want to show what's available, and then we'll just go.
I don't know.
Well, let's see. You got memory management, file systems. File systems, network. So.
Usually, you also talk about the boot block.
We'll briefly hit on the master boot record. So, if you want to maybe talk about partitioning up there. How many of you are fairly savvy with Linux, know what partitioning is, that kind of thing? I'm hoping everyone. Okay. Is there anyone that's not? Because I'd rather start where people can. Okay, so it looks like we're good there. Sorry, in Memphis I'm used to people not being quite as hip on technology. So anyway, I guess we'll turn it over to you guys to see what you want to hear about. But let's see. I don't see anything, that's huge there that's missing, but I'm sure there is. So, all right. So I guess it would be important. Where do you guys want to start? We're definitely. Do you guys kind of understand the basic structure of a kernel? Do you understand that there's, it manages resources at the very highest level of looking at it, and that when it comes right down to it, you're managing, CPU, memory, hard drive space. All of those things have to be managed by the kernel. And its sole existence in life is to manage those things and make it very fast to, to run processes that want to use those things. So I'm going to kind of let you, do you have a jumping off point that you want to go from? Okay.
Not really. The point of this first meeting is, as I mentioned downstairs to about, I think it's probably half the audience, it was that, but my first goal here is to figure out what you all are really interested in, okay? If somebody's got a burning desire to get deep inside of semaphores, or deep inside of, memory mapping, or, those sorts of areas, then, let me know that that's the area you want to focus on. And then you can take the lead on that area and work with whoever else happens to be interested amongst the whole crew here offline and online, you know, once a week here to talk things through and show us what you did and worked through and whatever, and then offline doing your homework while, you know, during the week. And then that's generally the idea that I had, was that hopefully the people with the interest in the different areas would pony up, you know, actually leading that portion of the review themselves. And I don't want it to be something where I'm, you know, bringing in guest speakers, this and that, but I do think that I can wrangle up a couple of people that are pretty deep experts in some of these areas. So if you've already scratched the surfaces, then when I bring them by, it's not on the mic anyway.
Yeah.
But after you guys have scratched the surfaces of the kernel, then if I bring these people in, then you can really benefit from it. Okay, so, you know, I've got some connections, not great ones, and when I leverage them, I want to be leveraging them with a half dozen people that really can learn from working with some of these guys. So hopefully we're going to have some interesting people pop up. No promises, but then that's part of the goal with the whole thing, is to try to, you know, show how just by goodwill of places like Google and the people that are part of open source stuff and all that, we can turn it into something that's awesome educationally for not just here, but going forward for everybody. So anyways, I'm happy to see you all have showed up. I want to get your feedback on things. So it's hard to do like a show of hands or things like that, but what I want to try to do is figure out, you know, out of the various different parts of the internals, where is your interest? Is it just general interest across the board to learn all of it, or are people interested in certain areas? I know that memory has changed a lot recently, and we had a speaker at SVLUG last month that was talking about how different it is to deal with memory as in software today than it used to be, because of the changes in processor speed and all that. You get so many more instructions per memory cycle, it's not even funny. So you don't think about software the same way as when memory was faster than the CPU. So those kinds of changes, really, yeah. We're going to blind you while you're trying to talk. Those kinds of changes to technology have influenced the source, the kernel, how it's organized, what its strategies are, and stuff like that. So I noticed some people, and some of the people that I've been working with, are interested in like why those changes occurred or where that's going or stuff like that. So that's kind of why I was trying to figure out and gauge what people's interest is, because I want to take this wherever you all really want it to go. So can I kind of figure out from, how about just most vocal and who wants to do what? And there, he's put a hand up. So.
I'd like to start off with a high-level structure. Understand the high-level structure and then work down. Possibly.
So he said that he wants to start off with the high-level structure and then work his way down. I'm going to kind of repeat what you guys say since there is no microphone, so bear with me through that.
Okay. Palmer?
I would love to see like how everything starts. Boot time. I'd like to see the handoff from BIOS to operating system.
Okay,
That's
so
Okay.
all right.
personal.
Now, do you
He's our boot loader team lead.
do you know much about bootloading and whatnot in general? Okay, so
But that makes it even more fun.
all right. So, do you have a laptop and the internet? Okay.
So yeah, Larry.
To learn now.
Right? Yeah. Okay. What I'd like you to do, if you can, is come up with like the top 5 bullet items of what you feel the infrastructure parts are that then everything else is based on.
Well, I think
then
that
the kernel, make a rough cut at it, and we'll cycle it around. We'll come back with a strategy based on that.
And we'll start kind of, I think that we can start from that, though. I mean, I think that it's important to start with this high-level view and see how it's structured. I think that when you deal with programs, that are all they're all compiled down into one, binary. You have the programs that have a lot of different pieces that kind of are modular and come together, and you have the programs that are very componentized these days, where you kind of isolate one piece from the other as much as possible. I think that part of what's important to know about with the high-level overview of the kernel is just that it's not componentized as much as you'd think, as much as a lot of these modern softwares for performance reasons, but it's not one monolithic piece. I mean, it is a monolithic piece of code, but it's not monolithic in function. It's monolithic in I guess it is monolithic in function. It's not monolithic in how you use it. So, how many of you have been exposed to kernel modules and trying to
Process-wise, it's
Excuse
not
me.
a monolithic process model.
Right.
Just one layer down from the application model.
So let me.
Think that the kernel was just like an app, only one layer down.
Okay, so I guess what you're gonna see in the kernel when you start looking at it from a very high level, it's divided into various subsystems, like what we were talking about over there. Things like, the scheduler, the file system that actually handles your disk, and you could actually make all these choices for the user and have one choice or very few choices. Linux takes the other choice and tries to provide an infrastructure to build whatever kind of file system that you want into it, build whatever kind of memory management, whatever. Some areas are more modular than others. So things like file systems, you have many different implementations of a file system. Memory managers, they generally stick with one implementation. I think that there's some play in there, depending on whether you're using an embedded device or not. But it's important to know that a lot of these systems have been designed so that you can, so that they're somewhat generic, so that you can kind of, plug in something else, and which is why things like the scheduler have been redesigned so many times. And that's very well reflected in the source code here. So this is the top level of the kernel source code, and you can see that it's, for the most part, directories. There's a few files that are interesting, like maintainers is the file where you go to find out who's maintaining a particular piece of the code, although it's gotten so huge lately that there's been talk about changing how that's organized. But basically, if you look at each of these directories, I guess I'll kind of lay out what each of these directories is for and tell you what I know about them. Documentation is exactly what it sounds like. It's a lot of documentation about a lot of different pieces of the kernel. And there's a lot of good information to be had there, but some of it's not necessarily completely up to date.
Take the warning, it can be a little misleading. Okay, you can go in and read the docs, and it'll tell you something works one way, and the source code says it works a different way.
Sir?
Not a lot, but a little.
So, you have a root directory. Can you tell us a little bit about why you went to that particular web page to start?
Okay, so I guess we should start before the kernel. Before the kernel, there was the resources to learn about it. Okay, so this particular website that I'm at is called the Linux Cross-Reference. The Linux Cross-Reference is a site that they have many different versions of the kernel, as you can see up here. Everything from 1.09 to 2.6.22.6, and each of those is a different kernel that you can look at. And it's interesting to look at some of the earlier stuff just to see how much things have changed. But what we're most interested in now is the current structure of the kernel. So we're going to be sticking with 2.6.22.6. That's very close to 2.6.23, which is the latest stable release. This site is very nice because when you go in and start looking at the source code, there's going to be symbols like variables and whatnot that are used. You can click on those variable names and it will take you to where they're defined. And it will allow you to jump around in the source code to see, when someone calls a function, what is that function doing? It allows you to click on the function name and get to the definition and figure out what exactly is going on. One thing that you'll notice in the Linux kernel, however, is that, it's multi-architecture. So, you're probably used to i386 and x86-64, and some of you with more experience may have seen things like Spark and PowerPC, but there's a lot more support in there, and there are architecture-specific things that have to be done. So, maybe dealing with the clock is different on each system. So, all of that's going to be separated out, and you'll find that when you're going in and clicking on a function, there may be, as many implementations as there are architectures supported in Linux. The other thing that you'll find is that there have been a lot of trade-offs made in terms of, selecting readability over, having the fastest implementation on every architecture, and that's simply so that they can be portable to more architectures. And that's reflected in the code, and, for better or for worse, some people, think that you should eke every single little bit out of it, and other people think that you should only enhance the most performance critical sections of code. And I think that Linux has made the practical choice here and tried to isolate out and mostly speed up the parts of the kernel that are most, that you're most likely to see. That you're most likely to have problems with, if there were performance issues. So, and that's done differently for every architecture because every architecture has different ways that you have to make these optimizations. So, I'm really kind of jumping around. Sorry.
You're doing great, man.
But anyway, so, and I guess that brings me up to that first directory, arc. So I'm pretty much going to be going through this site to show you what each of the directories do. Like I said, I'm not a kernel developer and never have been, and I probably couldn't explain a lick of the code in there, but I can tell you what some of the files do and whatnot. So, but what we're looking at here is the root level. If you were to download the Linux kernel source code, and you were to look at that source code, this is what you'd find. And so that's where we start. If we go down in here and look, you'll see things like arc and block and crypto and drivers and file systems. And basically, these are all the different subsystems of the kernel. So if we look at the very high level, we see a few things like which is memory management. So we also see things like block, crypto, drivers. So block, if you're familiar with Unix and how it kind of does the devices, you know that there are two different types of devices. There's character devices and there's block devices. And your character devices are things that, in a sense, can't be rewound. I mean, that's probably the best way to look at them because it's things like a mouse. You can't go back in time and look at what it was 5 minutes ago. But a hard drive, you can go back 3 blocks and see, what that block says. So that kind of looks at that kind of describes the difference between character and block. But the block things you're going to find more are things that you would put a file system on. So a hard disk, a network block device, like if you're familiar with iSCSI or something like that, or USB will be in there, but USB's kind of special-ish. Okay, so there's a lot of, yeah. So that one's hard to touch on because modern hardware has gotten really convoluted. There's no such thing as, there's this one type of device and it only fits one profile. And that's made things very complicated. And things like USB and FireWire and devices that are kind of meta devices, they tend to be split into a lot of different sections. So, USB supports sound stuff, and it supports, network cards, and it supports, sorry? No, I thought I heard someone talk, sorry. But it also supports things like, USB hard drives or thumb drives, so you can put a file system on it, right? So all of those different pieces are segregated into different parts. So you have the base stuff for USB is probably under drivers, so that's going to be things like your host controllers, the things that actually allow USB to happen, the equivalent of your RS-232 ports, right? Then you're going to have the block layer where you have things like, USB thumb drives and hard drives. That's where those are going to be implemented. And then you have, your USB sound devices are going to be under the sound subsystem. So it's fairly logical where things are located. And once you kind of, one of the hardest parts, I guess, with some of these meta devices is splitting them up in the proper way so that the right code ends up in the right places and that you have as generic a framework as possible and that it does everything that you want it to do. Okay, so some of the other directories up here that are a little more opaque. The crypto, there's actually a crypto subsystem in the kernel that has to do with performing cryptographic hash transformations and things like that. I think it also can encrypt and decrypt. There are some operations that it's very useful to have that in the kernel because you do either authentication of cryptographic authentication against the system or something like that. And the really nice thing is because these are software implementations, but then you can have hardware that actually accelerates all that, which can be very important on systems that require that kind of functionality. Moving down, drivers is like all of your hardware pretty much falls under there. Things like SCSI controllers and IDE controllers and SATA controllers and I don't know if RAID is under block, I think. Yeah, so because RAID is kind of a meta device, right? So it's not.
Okay.
So, but drivers for like your generic USB stuff is going to be under there. So the thing that you're going to find is, they tried to make things generic. If you're familiar with USB, you know that there's EHCI, UHCI, and OHCI. And UHCI and OHCI were both developed for the USB 1.1 spec, but there's common code that's used between them, so that will, it'll be pulled out and refactored into think of it as kind of a library in a way. The interesting thing to note about a lot of this code, though, is that, and most of this code, is that it doesn't look anything like what you would normally write, simply because, simply because they're dealing with a different set of constraints. They're working, in an environment where the rules don't apply as you know them. If you're, using memory in your program and you decide to access some wonky place in the memory, you can't do that when you're, in user mode. But if you're in kernel mode, you can do it. And so, they take a lot of precautions, and you also don't.
And it can be an extremely bad idea if it's the wrong memory location.
Right. But it can also, you can just, knowing that you can do anything, it's very powerful, but it gives you a lot of rope to hang yourself with, right? So, but what you'll notice is that there isn't like the C library or anything like that. There's, some kernel re-implementations of the C library, and some of them probably highly resemble what you'd see in the C library, but a lot of them probably don't, because they're either done in a way that makes them safer or makes them more performance driven, or they're developed specifically for a particular use case or something like that. So
support routines like print K and things like that. Right? So
well, there are things,
that's a perfect example. I think it's print K, isn't it? The kernel equivalent of printf.
Right. He's saying that there's a print K in there that is the kernel equivalent of printf, and print K is one of those things that has to be, there are parts of it that have to be implemented for each architecture, and parts of it that have to be, and parts of it that are common to all architectures and whatnot. And it looks more like a subset of printf than the whole of printf. There's a lot of functionality there, and what it's for is basically printing out log messages from your kernel to user space, but it has to support, it has a lot of different requirements. Like, for instance, it needs to be able to print a message to the screen as early as possible, because if you can't get those early debugging messages, you might never know what went wrong with your system. And it has to support, serial connectivity if you're connecting over a serial console, and it has to, and there are subsystems to initialize your video that have to be initialized before this can happen. But we actually want to get messages before that, so it has to do some, half-assed version of initializing your video, and then it can write those things. So those requirements just don't exist in user space because we can depend on those things to already be set up. It's the same way that when you're booting your computer, when you first jump from a bootloader into your OS, you cannot rely on certain things to be set up. The best that you can do is you can rely on the fact that you're probably in 16-bit mode, and your hard drives that are detectable by the BIOS are probably accessible by PIO, and hopefully you have enough. If you're on a PCI system, hopefully you'll be able to enumerate the devices and figure out what they are. But I mean, these are problems that you just don't have to deal with in user space. So it's much lower level, and whatnot. Okay, so moving on, IPC is inter-process communication. If you're familiar with things like piping the output of one command to another, that's inter-process communication. Things like sockets, when you're network programming. Things like, I'm sorry?
Shared memory.
Shared memory. If you're familiar with System 5 shared memory, that's used to stop from having to copy from one process to another. They just use the same memory space. I believe there's things like semaphores in there and whatnot also. We can go in and... So... Our...
Sem.c.
Yes.
My favorite slabs is kernel code.
Right. Okay, so does anyone have any questions about the different directories here? Because I'm kind of just going in order of what I see.
So where are the test cases for the kernel kept?
Test cases as in unit tests?
Well, we got a bunch of code up there. Usually you have to have a test harness, and you want to, so where would you learn about how you test the kernel?
So there's a project out there that is independent of the kernel called the Linux Test Project. I don't really know much about it, but I believe that would be more where you'd look for testing. I mean, it's going to be tested a lot like any other system. So you're going to isolate a function. You're going to give it, inputs that you know how it should react to, and you're going to test for those outputs. And you would probably end up looking at it more like a user space program at that point. But I really can't speak about that in any more intelligent way. So there was another question. You?
Yeah, I was just going to ask which directories here or modules are pretty much constant between architectures, and which directories here change the most between architectures. Obviously the ARC maybe is obvious, but I don't know about the other ones.
So everything else, everything except for ARC is actually generic code. So they have done a very good job of isolating that code into the ARC directory. When you're in the middle of building Linux, it will symlink one of the ARC directories to the current architecture and include all the right things. And so when you're developing, essentially, the ARC code can override things that are in the generic code, but everything that you see in those directories is generic. So I guess this deserves a second to look into, but I mean, these are some of the architectures that are supported. Everything from, so we have everything from like, Alpha and ARM26, and we go all the way, I'm sorry?
68,000s, I love it, with no MMU.
These right here were,
this one right here.
yeah, that one, I'm not going to talk about that because that's actually very different from the regular kernel. The original kernel was designed with the idea that there was a memory management unit, which is what an MMU is. This kernel was, designed, sorry? Well, it was designed, actually, I believe that the original use case of this one was for the Palms, wasn't it? The no MMU one? I thought that it was, and I may be wrong about this, but I think that the no MMU one was actually when they started the handhelds project and they were trying to port Linux to extremely embedded devices. They were trying to port it to a Palm device, and I'm pretty sure that's where that one came from. And that's where the that's where a lot of your embedded stuff comes from, because when you're dealing with an embedded platform, you're dealing with things that may not have a memory management unit. So when you get your WRT54G, I don't think it has one, and it has something very related to that. Go.
It was a little earlier than that in terms of its origin. It might be for the Commodore CG32, which used embedded version of the Motorola 020, which naturally does not have any memory management, but Commodore shipped a whole bunch of boxes using an EC chip instead of a regular CPU.
This is why we don't let them out very often.
I cannot speak to that part of the kernel because, frankly, I don't care. But
That's even better.
so, but I will say that the architectures that are most common these days, your i386, which has actually been recent. There's an AMD. It's not separated. Maybe it was already combined by that time, but. They actually combined the AMD 64 and the i386 into one architecture now, which was a very radical move considering that one was 64-bit and one was 32-bit. That created a lot of havoc.
Page down so we can see what's below S390.
Yes. So, are there any architectures that you're curious what they are? I might be able to answer some of them. I can't.
What's an SH?
An SH is a yeah. It's the old. Remember the little jornadas and stuff that you could.
There's an x86 64 down there.
Yeah, so there you go. So they named it. They must have named it the generic thing, right? Because they were trying not to step on anyone's toes. But certain projects called it x86 64 because they didn't want to be AMD specific. Certain projects gave AMD the credit for developing the first 64-bit architecture and actually named it that. This version of the kernel doesn't have that combination. The 23 kernel. Actually, those architectures have been combined. And that's another example of refactoring out code and trying to make sure that
Except for the virtualization subsystem stuff. There's still...
Well, there's still stuff that is separated in them, but that separation goes under that directory. It's not...
Virtualization goes on the board. Virtualization.
Virtualization goes on the board? Are you sure about that?
I'm not so sure about that.
Okay, well, you said it.
Well, we can talk about virtualization and how it works. But yeah, go ahead and put it up there. But
He's in charge of the virtualization team, okay?
we'll see. So a number of these architectures are very old. I don't even think that SH is developed anymore. There's actually a Debian port to it. is a really interesting port. That's Linux ported to Linux. So
What's the
Well,
difference
user mode.
between RPC and PPC? RPC and PPC, what's the difference?
I don't know. I imagine that one is probably older school and one probably has support for 64-bit and some other things. I really don't know. They may be in the process of renaming it and moving the stuff over. I can't.
Is that from UML, user mode Linux?
Yeah, that's what I was going to say. Yeah, so I honestly don't know the difference. I'm sure it's somewhere. is an interesting one, though. That's actually Linux ported to Linux, which doesn't make much sense, but you can actually run Linux in user mode in order to test various things. So that's one way that you could hook up a test harness to it. Like I said,
Kind of.
well, it was kind of the first step in virtualization because it wasn't real virtualization. It was just basically making it run as a process, which there were a lot of, basically porting it to a user space environment is very different than running it on bare hardware. So that required a separate architecture, but once you get it there, you can actually run it and have virtual terminals. I think that it runs an X or something. I really don't know much about UML, but it was one of the first attempts at kind of strictly isolating processes from other parts of the system.
Sure can't VNC into them or something.
Yeah, I mean, there's a lot of things that you can play with in there, and I really don't know much about it. So, but what I can say is, what I do know is that was one of the first steps in really isolating things and trying to do that. There are other things today like Zen and whatnot, and I think that Zen has actually been incorporated into the latest kernel. There's another one called LVM that's been incorporated. I can't really speak very intelligently on them, so I don't. But the nice thing about this whole structure of the code is that everything that is machine specific, that is, architecture specific, is separated into those directories. And I thought, so when you build the code, there's actually a directory or a symlink that gets created to one of these. If you're building for an i386, that symlink will point to the i386. And when you start looking under here, you'll notice that there's a lot of things.
You want to, if you do
There are
anything that's cross compiling, like to different target architectures, watch out for that symlink.
You're saying watch out for the symlink if you are compiling to another target architecture, because if you were compiling for one and then you switch around to compile to another, or even if it's your first compile and you don't know what's going on, of course by default it's going to try to compile for the architecture that you're on, so it can obviously cause some hair pulling if you don't know what's going on there. I'm not even going to discuss cross-compiling or anything like that because I think that's a completely other topic. Okay, so I'm sorry?
User, what's the user directory? That's what he's asking.
I don't know, let's look. I think I know what's in there, but I want to make sure. No, I don't know what that is. Oh yeah, I do. Okay, so this, I believe that these have to do with, do these have to do with the early user space, like the, I'm not really sure, but I mean, we can open it up right here.
Yeah. This is how nice the thing is for reference.
Press boundary, that is fine.
Well, of course it's shown.
It is early user space. Damn, I'm good. All right, so what it looks like this one is doing is, it looks like what this is doing is it's actually taking the built kernel and attaching it to the init ramfs, which that gets into kind of boot process, and we're not really there yet. So I can't speak intelligently directly on this, but we'll talk about how the kernel actually boots, like kind of how it does it today and how it used to do it, and why it does it like it does today. The lib here is library functions that are used in a lot of places. So things like, these are actually implementations pulled from zlib. So it does some compression in the kernel that is useful to have the library in there. Things for, well, we'll get to the init ramfs, but it uses the zip code. So let's see. And scripts are just utility scripts that you use when you're developing the kernel. So there are things in here that will, complain about your code if it's not in the right format, or re-indent it the proper way, or so. The what? Oh. Yeah. And a lot of these are just undocumented scripts, unfortunately. This is probably something that tells like the change in the number of lines from one kernel to the next or something. And, let's see. I'm sorry?
Where's the scheduler?
The scheduler is located, okay, so I guess we'll move on to the kernel directory then. So the kernel directory is where all of that happens. So you have the basic pieces of the kernel, things like process accounting, here's, I guess, a generic view of a CPU, DMA, how it looks in the generic, and then if you get down here far enough, I think this is where, sched.c here. So this is where the scheduler is actually implemented. I really can't speak much on the scheduler, but I cannot speak to the specific implementation of the scheduler, but I can speak at a very high level of what schedulers do. So is there anyone that doesn't really understand scheduling and what it's for? Is there anyone that hasn't? Go ahead.
No, that doesn't.
Okay, so fair enough. So when you're using an operating system, you have a lot of programs that want to run at the same time. But when it comes right down to it, you only have a finite number of resources. So you have to basically prioritize those so that the things that are highest priority get the resources they want first, right? So the scheduler is basically where all that happens. When you run a process, it runs with a certain priority, and the scheduler, it gets, you hand it off to the scheduler, and the scheduler decides where in that line it ends up. And schedulers can be very simple, where you just throw something at the end of a queue, and in like a real queue of people, except for people that jump ahead of people. But you could have just a line where you just pick the next one off, and that's not a very smart way to do it, but that's a very basic way that you could do it. And the Linux kernel is substantially more complex than that. It has a system of priority queues, so that it has more than one queue. It tries to push, if you're at a certain priority, you get pushed into that queue, and then everything in that queue that's before you gets executed before you do. And essentially it gets pushed on, and then it eventually gets executed. And the thing is if you're very low priority, you could be starved for a while, because there are things that are higher priority than you. And this has actually caused a problem with certain applications. So people are starting to do something called real-time computing with Linux. And that's something like, I'm running my industrial process and I have to respond to this event within 25 milliseconds, or else I lose a $25 million piece of machinery. And that type of hard real-time event, if you don't respond to it that quickly, that it has real consequences, that is not guaranteed in the Linux kernel at this time, I don't think. There's some real-time stuff in there, and I'm not exactly sure how far it goes, but it's not where people want it for that kind of application. So a lot of the times that you see, embedded devices running real-time stuff that are running Linux, they're either soft real-time, meaning that they don't have those kind of hard requirements, or they have special patches on them, meaning that someone's introduced new code that is not in the mainline kernel. And and I think that pretty much, that's about as much as I can really speak about the scheduler. It's basically the core. It chooses what goes next, and it can be the difference between your system being very sluggish feeling and being very responsive feeling. And, if you're choosing the right processes at the right times, then the right things will be executing at the right time, so that the least amount of wait has to happen and the perceived function of the computer is as good as possible. And needless to say, you would be able to, schedule in different ways, and those different ways may be better for one application than another. Go ahead.
Do you know what file main.c is in?
It's in main.c. So it's under kernel. This is basically where it all starts, under kernel here. But I thought that it was under here, maybe not. Okay, I guess I was. Another piece. Oh, it's an init, I'm sorry. So there's main.c.
Can you show us how to trace cross-reference? Can we search for a symbol or something like that?
Sure. So let me show main real quick, and then I'll do that. So wherever main is. Yeah, I thought that I would come across it faster.
It might be at the bottom.
Yeah, that would be too.
Very last line.
That'd be way too obvious.
Of course it's
Okay, so it's not in there.
I'm not sure there's actually an actual main. See, main's just a convention. CRT0 is actually like what gets.
No, well, okay. So here's what actually happens when
Or at least it was.
C has a convention that main is the first function that gets called, but really what happens when your program gets loaded in an ELF binary is it calls setup, I think, or something like that. Setup, I think. Is it called start? Okay. Start.
Right, yeah, there's like an entry point.
But there's
in the older compilers, it was called like _CRT0 or something.
Yeah.
It was like this entry point where there was actually before main.
And
it would set main up and
right, it would set up the whole environment for a C execution environment. So it would set up your stack, it would set up your program counters, it would set up all of the stuff that has to be in place for a program to actually run.
So where does start?
Which of these is called?
That I just saw here.
Where's the code at the beginning? He wants to see the beginning of the kernel. There you go. Where does it start?
It must not be start, hold on.
Because it really doesn't start anywhere, does it?
Well, it does, I mean,
It has to move from somewhere.
yeah.
It's gotta have an entry.
It's actually inside every object.
Oh, is it? Okay.
It's under render setup. Is it per architecture?
Yeah, actually inside I386.
Is this it?
Workable computing. 9787 of main.c runs on Init kernel on that, isn't it?
Yeah, I think so.
I think that's just.
But there's,
I don't know if
yeah.
there's actually a main.
Here.
Here's post. Init post.
Where's that? Where's the init kernel? Is that under here?
748 in main.c.
748.
Slash init slash main.c.
748. Okay,
you go.
so
Yeah.
that's a net post, but that's
And then right below that, there's the kernel on it. And that's
yeah.
that's early in. I'm not sure if it's exactly.
This is super early. Basically, when you're booting your PC, this might be a good segue into kind of how a computer boots, because every architecture boots a different way. And if you're booting into 32-bit mode or into 16-bit mode, it jumps into a different part of the code so that it executes the right instructions to flip it into 32-bit mode and go on. So, but basically, I guess this is another example of the rules don't apply in the kernel, because, you know, main.c, yes, this is main.c, but main is not necessarily your first function, because instead of the C environment setting it all up, and instead of you including that normal piece of code that gets included in every C program, they're having to do everything themselves.
Yeah, like none of this code actually includes like studio.h or anything like that either. You know? I mean,
Right. Yeah, so, I mean, like I said, not a kernel developer, but it's important. I guess the most important lesson from this is just that there isn't the initial piece of code is not defined in the same way that you think that it would be, because what happens when you're compiling a user space program is there's a lot of behind the scenes stuff that happens when you say GCC, you know, main.c. And basically, it will not only include your function, but there's also a lot of boilerplate crap that gets included in there that does not get included in this, because they specifically don't bring it in, because it's not a user space program. So yes, it gets compiled into an ELF binary, but it does not.
It's not like loadable.
Right.
It's not even a loadable binary like you would think of a regular runnable.
Right. I mean, it just won't. It will not function in the traditional way, and I really don't know more than that. So I'm happy for anyone else to raise their hand and talk about it. So.
How can we find out who called this one?
How can we find?
Who calls this one?
Okay, so we can find out who called these functions. I mean, basically, I see this function. Here's the definition. But if I click on it, after it comes up, basically, I see that it's defined here, and I see. I see there's a function prototype in main.c, so there's a prototype and the function definition, and then down here it tells me where it's actually used. So that's not even the head, that's not even the top. Here, let's just see. Okay, so.
Well, the caller for that was 431. If we back out the caller chain, some line 431 is like the only one left. So that
Yeah, I'm not. A lot of the functions that are getting called in here are actually defined in the architecture-specific code, and they're doing things like setting where to start execution from, and it gets very complicated and very architecture-specific. And to be honest, I really don't have a strong understanding of this, so I can't do much more than clicking around. But I figure we can try this and see if maybe we come up with a main. Let's see.
So I was looking at the architecture because there's a lot of like static defined.
Yeah, but there's nothing that's jumping out at me as main for every architecture or something. So it's saying that it's referenced in here. So anyway, It's fairly clear that it does not start at main. I don't know exactly where it starts. There's a bunch of linking that, sorry?
Something called start kernel.
Where is that? Is that in main? Is this the one that we just looked at, I think?
Probably not in the source.
What did you call it? Start kernel? Start? No, I'm not in the file, duh. Okay, so this looks pretty early here because here's your command line and yeah. So
If you look that up, it's only started from the
Yeah, that's a
yeah, so this is from the architecture here. Okay, so
comment there. It says do this as early as possible, so you know they put code in there on purpose. That early, so.
so this is probably referencing something that does very architecture-specific things, like probably setting up the right first block in order to get executed and things like that. I can't, like I said, I can't really speak intelligently on that, so I'm not going to. Okay, so, but what's interesting to note, and that you'll see up here, are things like it's a void function. They're taking the command line in. This is actually your command line, I would imagine, from when you do your kernel boot. The stuff that is set up down in here, and probably some of these pieces also, I would imagine that a lot of this has to do with, setting the right memory locations for things, because when you actually type a command line in at boot, it gets stuffed into a particular location in memory. It knows to read it out, and that's what a lot of this stuff is. But anyway, I think it's would be prudent if we moved on, because I think we're spending a lot of time there. But and hopefully we can get some people that actually have a deeper knowledge of this stuff to come in and maybe speak of it. But let's see.
Where are system calls?
System calls, I believe, are under sys or something.
Most of that stuff now is like with device driver.
Well, except that system calls,
APIs now is through /proc or whatever.
but you don't make system calls into device drivers. All that stuff is in kind of core-ish code, so it's in like, I didn't mean to go there. It's kind of in subsystem code, but if you're talking about are you talking about how is a system call implemented, or are you talking about where are all of the system calls?
Where are the system calls?
Like open and lseek and things like that. Those it depends on the subsystem. If you're using block system, system calls like read and open and things like that, those are going to be in the block file system, in the block system or.
Like fork, like exit.
Okay, so those might actually be in kernel because those are pretty core things. So there's fork right there. So a lot of these core things are going to be, very, very core operating system things are going to be in this kernel directory, just because they're things that the kernel needs. But you're going to find that there are things like, in file systems, there's a virtual file system layer that sits above all the file systems. So when you implement a file system, you make it conform to a particular interface, right? And that interface is called the VFS. And that VFS provides other system calls, things like, open and write and close and things like that. But it really depends on the subsystem. A lot of things that don't fit into another subsystem go under kernel because they're very core things. If you're familiar with operating systems, you know that there are some operating systems that do a lot less than this, and there are some that do a lot more when it comes to what the kernel actually does for you. There are some systems that fit into a couple of cache lines, and and all they do is provide a very minimal amount of inter-process communication. And then there's things like Linux, and then getting way above that, there's things like some of the other systems that are out there. So okay, so So I guess now is a good time to talk about kind of how the system boots. There's actually, so how many of you are familiar with how a system boots? Just like going from like bare metal to kind of the process and what components are involved. Because what'll happen, what actually happens when you start booting a computer is you don't actually hit, it's not actually as bare metal as it could be when the operating system gets a handle on it. What time are we? Almost 9 o'clock. Hey, when are we stopping? So, I mean, I'm sure that all of you have heard the term BIOS, and yeah, we're getting out of there. So, I'm sure that most of you have heard the term BIOS. You know that your motherboard has all kinds of components on it, and so have our BIOS. Under here we have something called the ISA. And then the ISA is the instruction set architecture. It's basically the instructions that you program to program the system. It could be the Intel instruction set or the Spark instructions, but you're going to have some kind of firmware that sits on top of that in order to make things available like hard drives and very basic devices, because how else are you going to boot if you cannot access your hard drive to get information off of it to actually load something other than what's in the chips on the motherboard. So as you boot your computer, it comes up through the BIOS. The BIOS does some initialization and eventually hands off to your OS. And the reason that I draw it like this is because your OS is also going to talk directly to the ISA. It's not going to talk just to the BIOS. In fact, in a lot of cases nowadays, it's even bypassing the BIOS almost entirely. Although newer generations of firmwares and BIOSes are actually changing some of that, which is how it should be. But so then you have kind of your user space, right? All right, so as you move up, and actually this is going to be talking to the ISA also, but not really as directly, so this is really bad. I mean, basically what I'm trying to show you here is that every layer talks to the layer below it, but there's not as strict of an isolation as you would like. Now, from the operating system, between the operating system and user space, there is some other hardware that makes a strict separation of certain operations, but you're still able to talk directly to the processor for certain things. It's very controlled how you can talk to it, so that's the way that they kind of keep memory, keep programs from stepping on each other with regard to memory accesses and whatnot. But when we turn on the computer, all that we have are, you have your memory sitting there, but you don't know how to access it. You don't know how to access any of your hardware. So it comes up, and in your BIOS, there's actually a place that it sits in your memory space. So when you're programming and there's a particular location in memory where you always find the BIOS. So when your computer comes on, it knows where to find that code. It starts executing that code through the BIOS, and then that BIOS actually starts doing things like reading it initializes your hard drives, initializes your memory, makes sure that everything's good in some cases, and then it starts handing off to the OS. And that's where it actually, it'll talk to your hard drives. If you're familiar with the master boot record, is there anyone not familiar with the master boot record? Please raise your hand. You. All right, so.
There had to be one.
Yes. So your MBR, or master boot record, is something that's the first sector on every hard drive, right? So by convention a long time ago, they decided that your MBR would have to look a certain way to give information about the hard drive and how it's laid out, right? So when you go to partition a disk, in your MBR, there's a piece of it called the partition, the partition table. There are some other alternatives now to the traditional partition table, but in essence, there's always something that's going to define how the disk looks. So it may look a little different than this nowadays, but there's a very particular format for this sector. And what happens is, in order to be bootable, they have to have a number written into a certain, I don't even remember what the number is, but there's a certain value they have to have written into a particular part of the sector. And then, sorry? 55AA, thank you. So 55A, what location?
That's a very last location.
I'm sorry?
Last location in that sector.
Okay, so the very last location in the sector has to be 55AA. And if it's not 55AA, the BIOS will not think that it's a bootable drive. So you'll get, if it happens to be the only disk on your system, you'll see an error like, operating system not bootable or something like that.
So the PC architecture thing, other architectures, BIOSes are smart enough to understand the file system and actually boot into a file from a file system.
That is true, some are, but I am going from a PC-centric point of view, but there are some firmwares out there that rather than reading, they'll do a lot of this, but they actually are much more functional than the BIOS in that they will also understand certain file systems. So instead of saying, boot from this drive and reading the master boot record, instead what it does is it says, I want you to boot from this file system, and then you can actually, on some of them, even go so far as to pick out where on the file system because it actually understands the file system. If you have ever played around with an IBM RS-6000, they actually understand FAT. And I think they also understand whatever their, the JFS or whatever. And when you're booting a kernel out of those, you actually give it a command line that says, boot a kernel from here. It looks a lot like executing a program from your operating system or something. And those types of systems, I think, are a lot more fun to play with, but they aren't as common as PC. So yes, you're right.
I think Grub knows file systems, right?
I'm sorry?
Grub knows file systems, although if you put that on the master boot record, you can go looking for...
Yeah, that's how Grub works. It's a tiny OS. And there are some file systems that it does not know.
That is true. Okay, so he said that Grub knows file systems also. So what happens when you have Grub loading? There's what's called the stage 1 part of the bootloader. Your bootloader on a PC, for very legacy reasons, has to fit into a very small place. So what happens with Grub is it will actually load that first step. Then it will actually load a second and possibly even third step, depending on the file system support that you have and the functionality that's included. But it can initialize such that it can access parts of the system that it couldn't access under just the BIOS initialization. So Grub is best thought of as its own little operating system, right? So it comes up and it gives you, it basically is an operating system that has the functionality of looking at certain file systems, doing certain other very basic things, and executing a kernel in the way that Linux thinks that a kernel should be executed. And there's another thing called the multi-boot, which is actually pretty neat, but it's never been really taken up by anyone, unfortunately. But what is happening there is you have it moving into the BIOS, and then the OS, which I'm really kind of including this, this bootloader stage. So you were talking about how certain firmwares actually understand file systems. Some of those firmwares don't necessarily understand all the file systems that Linux would support. So you could potentially put a bootloader on there that would understand more file systems. It still might be useful in that case. Because the firmwares generally aren't updated as often as a Linux kernel. So. In fact, Grub has actually been ported to some other architectures for its next version. So once you move up through the bootloader has a property that once it loads the OS, it completely destroys itself, which is good because it means that you don't lose memory to the bootloader that can never be used. And then the OS starts loading, and Linux has a property where it returns all memory to the system that it doesn't need during the boot process. So unlike some Unixes that came before it that wasted small amounts of memory, Linux is allegedly better in that respect. you can argue the merits of one over the other all day, but that is one thing. So once you move up into the OS, though, it provides you an environment to actually run in, and once you're running in that environment, you're in user space, and you can make calls into the kernel, and those calls could make calls into the BIOS, which could make calls into the ISO. So, I mean, everything just kind of stacks on top of one another. I don't know what just happened over here. Okay, so. That's a very high-level view of how, it's kind of a mid-level view of how it works, I guess. But is that pretty clear that you kind of go through these different components? They kind of hand off, through some kind of handshaking protocol, some formal, way of handing off to the next layer. And then that next layer kind of takes over. And it's, when you get to the OS, it's much different than working on the BIOS, but it's still very low level, and then user space is what really presents you with everything that you need to, to really do your job. And these distinctions, there can be many more layers or many less layers, within the OS, and that's really where you get into, like, people talking about, how well designed an OS is or whatnot, and debating the merits of different kind, microkernel versus monolithic kernel and all of this, and all of those decisions can affect the performance and and other properties of your kernel. Sometimes performance isn't always the number one priority. And but this is where, like, your Linux or your or your FreeBSD or your OpenBSD or anything like that fit. And I think that's about as dead as I can beat it. So all right, so anyone?
So when you're talking about BIOS, I guess every once in a while BIOSes get updated?
They can be.
And how important is it to get the latest? Or that's not a big deal as long as you're booting correctly?
Well, think of a BIOS as another piece of software, so they clearly found some bugs that they're trying to fix. The question is, did they break? Did they introduce other bugs that are going to hurt you? So. Well, it depends on the company. You'd have to go to the manufacturer of your system, and it depends. Some companies, I'm sure that Dell probably uses their own product, so I'm sure it's a matter of looking in the right cubicle. Whereas, where if you're working at FedEx or something, you have to go to Sun, or whoever the vendor is. If you're running an AIX system, you have to go to IBM. And back in the old days, when you couldn't just update a BIOS, there were companies that actually sold the hardware chips that you could use, and there are still companies that do that. I can't think of any good reason to use them other than data recovery. But these days, it's fairly common for your vendor, if there's a serious bug, they will post a replacement. Sometimes sometimes some of the companies don't provide all the functionality that I'd like to see. Like, I don't think that you can boot from a USB thumb drive on my laptop, which I think is stupid. But you've been able to do that for 6 or 7 years, and I've only had the laptop for 2 or 2.5. So anyway, actually it hasn't even been that long. Go ahead.
On your laptop, have you tested giant floppy mode? Because mine will not boot from any USB device unless it's built in giant floppy mode.
My BIOS does not include support for booting from a USB device. It's not the type of BIOS doesn't have support for it. It's that Gateway decided not to include that functionality in their build of the BIOS. So the thing that you have to understand about,
Some people consider that a security threat. Like if someone,
it's my laptop.
someone at work decided to boot your laptop with a copy of Linux and NTFS, and then they could just read.
If they've got physical access, they've got it anyway. Why don't they just take out my hard drive and take it home with them? I don't see that as a valid argument. So, basically what he was saying was that someone could come up and boot a copy of Linux on my machine and Trojan my machine if I allowed them to boot from a floppy or from a USB device. But there's no reason they couldn't use the CD-ROM or anything else to do that, or even boot from the network, which mine supports. But it doesn't support booting from a USB stick. So basically the way that a BIOS works, though, in most cases is that the vendor will go to a vendor of a BIOS. They have to license that BIOS, and then they have to adapt it to their systems. And it's a very low-level thing. I mean, it's, you know, things like initializing your memory. You know, things that you would never even think had to be done if you've never programmed in that level before. So
what's the story with OpenBIOS? I think
OpenBIOS is totally sweet. OpenBIOS is not supported by anything. I mean, OpenBIOS basically. Are you talking, which one are you talking about? Because there are a number of different.
Linux BIOS.
So Linux BIOS, you know, GNU is running their systems on Linux BIOS systems, right? And I don't know if they're running extremely old systems or what, but the systems that actually run Linux BIOS, to my knowledge, there's nothing modern that runs it. And anything that does, I mean, I would totally run a system with it because they can allegedly boot to Linux. They skip all of the normal BIOS configuration stuff because Linux does it anyway. And you can get to Linux. You can actually get into the kernel in less than like a quarter of a second or something. And it's, you know, it's a really awesome thing, but no one's supporting it. You know, for whatever reason. I mean, it may be that, you know, these other companies that have BIOSes that they've tweaked over the last 20 years, they know that a Phoenix BIOS is going to work like a Phoenix BIOS is going to work like a Phoenix BIOS did, you know, whenever. Whereas if you go with Linux BIOS, there are potentially bugs that haven't been addressed yet.
Yeah, that was actually the issue because it came up at a conference, and one of the BIOS developers said that they showed the BIOS to basically there's several open BIOSes. One is the open firmware that Sun offers, which is not Linux, and then there's the Linux BIOS. And neither of them were liked by the motherboard makers for the very reason that you said, is that they don't know it. They know all the bugs of the BIOSes, and sometimes people like old buggy software if they know where all the bugs are. It kind of makes them feel comfortable.
Job security.
No, they know it's there, and they're happy that everyone's better.
Well, I mean, you know, you have to understand where they're coming from too. I mean, that has to be an extremely reliable, and at the very least, you have to know what the problems are when, you know, when there are problems. Basically what he was saying was that, if you didn't hear him, was that a lot of the vendors don't want to use an open BIOS because the BIOSes they've been using for the last, you know, 20 years or so, 25 years, I guess, they know where the quirks are. They know what the problems are. And it's not that you couldn't get as good a support for one of these other BIOSes, but the problem is it may take longer to bring a product to market simply because it has bugs that haven't been flushed out yet. Yes?
Well, in this industry, we seem really big on propagating obsolescence. It drives me nuts every time when I see some loop in C where they start at 1 and they go to N. The language is set up so that it's very efficient when you count down. And it's some guy who is senior in the organization said, no, we're going to count from 1 up because that's what I'm used to because I learned Fortran and I'm in charge.
He's talking about how he is totally tired of old suits making, or old tech fogies making decisions based on what they originally learned and don't want to relearn. And, you know, that happens sometimes. That isn't always the case, though. I mean, the thing is that there are real business needs. And if you can say that you can ship something, you know, faster, better, quicker, you know, with, you know, by using one of those BIOSes as opposed to using an open BIOS, then, you know, that means a lot to in an industry where shipping a product first means something. I'm not saying that I agree with it. I think that, you know, if some of these companies would spend, you know, a couple of seconds on, you know, some of these open alternatives, I think that they could turn into something really awesome. But it's like, you know, I mean, I can't explain why they do it other than it's just kind of momentum, and changing the direction of that ship is, I mean, you're changing the whole industry. It's not just one company, and they're huge companies. Go ahead.
I just spent a year at a chip company that works in the PC server industry, and amount of work that you had to do to get a chip onto the motherboard of a modern, like a mainstream high-end server.
Can you come up here and say this into the mic, actually? Is there, where's the AV guy?
Just go ahead and
Can he talk into the mic on here?
go ahead and talk to me.
Right here.
Thanks.
The amount of work that it takes to get a chip onto the motherboard of a modern high-end server. The company that I was working at worked with HP, Dell, and IBM on a series of different designs. It resembles nothing quite so much as air traffic control, like at a busy time during the holidays. They have to plan to sell millions of units, and when they start planning backwards, they give you a small amount of real estate to put the chip down. If it's going to be supported with Linux, which a lot of them demand now, then you have to get your driver completely QA'd and debugged and into their hands long before there's really any good reference prototypes out. So my challenge was always getting machines that did not resemble the physical hardware and then trying to trick the kernel into making it think that that was really the thing that you're going to run on. Bug by bug, you would try to zipper this all shut, but the whole time the clock was counting down. Your code was going to ship, the production lines are going to start, and if you miss the boat, then they mark you as a company that does not execute very well, and they kick you out. So there's not very many chip companies that can play at that level. You've got your NVIDIAs and your Broadcoms doing video and network design, and when it comes down to doing non-standard designs, you'll find that at many levels of the business, right down to the top of your head as a technical person, there's a very low tolerance for risk. Very, very low tolerance for risk. The airplanes that you fly in at Thanksgiving, they might be able to do all kinds of tricky stuff, but do you really want the pilot to be doing that kind of thing while you're on final approach? That's what it's like trying to design the motherboard. It's like, I don't know, it's like 15 months. It's like 18 months of final approach.
Thank you very much. Are we back?
He's in charge of our low-level chip design group.
Yes.
How does the boot process change when you're booting over the network or a USB drive?
Okay, so the boot process is still kind of abstracted away. So I said once you get into the BIOS, it starts trying to, load your hard drives and whatnot. The BIOS actually has to have support for booting from a USB device. And the USB specs and those more, complicated specs do make some provisions for, boot time things so that, you can more easily initialize, a hard drive over the USB bus. It might only work on, not through a hub. It might only work if you're directly connected to, the hub that's inside the computer and only under certain circumstances and only from certain ports. But essentially what happens is the BIOS has to have code in it to initialize that drive, and once it initializes that drive, it can access it through the BIOS calls. So there are calls in the BIOS. Think of it as a programming API. I mean, there's a way to access the drives that the BIOS knows about, and the BIOS, if it knows about that drive and has the capability to boot from a USB drive, then you can do it. I mean, it's all about abstraction again. So. Yeah.
Let's wrap it up.
All right.
What I want to try to do is actually get a couple of different people to put their hands up and be the leads for various parts of the stuff. I've made a couple of jokes about it and all that, but I'm kind of serious.
Well, why don't you come up and get some talking to the mic?
Can't I just yell?
No, you got to talk into the mic.
For posterity.
For posterity.
That's right.
So, semi-joking, earlier I talked to a couple of different people, said they had interest in certain areas, and I was like, all right, then you're in charge of that area. And I'm kind of serious about that. I'd like to have, a handful of people that are intent on being here for most of the meetings, if not all of them, who have interest in whatever aspects of the kernel to take on a leadership role with respect to diving into that aspect of it. So, for example, Larry had talked about, what are the higher level aspects and things like that, and you got your marching orders on that already. So let's, so then for each of these different parts, if you have an interest in memory management, by all means, let me know that. If you're interested more in scheduling aspects and pros and cons of versus changes of the scheduler strategy over time, that's also stuff that's interesting. And if that's your bailiwick, then let me know that. And if you are hesitant about it, just realize you don't have to be up here, you don't have to be talking to the whole crew. It's more about contributing to the strategy and the direction and the depth of understanding of that particular aspect of the code base than it is about your social skills or anything else. So I know some people are hesitant just because they couldn't just stand up here like I do. And that's okay. It doesn't matter. So I welcome you to contribute via email, via actually coordinating with other people for like subgroups or whatever. Standing up here doing like Warren did if you're ready to do that at a certain point about a certain part of the kernel, etc. So, and I'm hopeful that this is going to turn into something that gets some ongoing life. The once a month SVLUG meetings were fun, but it doesn't get much momentum. It's kind of like start, stop, every month, start, stop. So this is going to just be rolling, and then we can make it whatever we want to make it as a group. I can't and I won't just do all of it. Okay, it's all up to everybody. So pony up and we'll make it all fun. Okay. Thank you to Warren for coming through because dude. On a moment's notice too. And
that's how I do it.
Again, I can't promise things, but I do have some people that are some heavy duty players who, if they're properly motivated, can really give us some insight to some of these things once we're ready to listen. Right now, we're not there. And once we understand some of the piece parts, we'll be at a point where somebody could talk to us about the strategies and things. And that to me that's where the real interest is, once we get under the hood, we could start looking about why did they design this way versus that way. And that kind of stuff that's my interest in it, is where's the kernel going longer term and things like that. So hopefully we'll get some of that insight too going forward. All right.
And remember, this is...
I don't know. We'll see you in 1 week or 1 day. Tomorrow night is our monthly meeting. The Silicon Valley Linux User Group monthly meetings are at the Symantec V Cafe.
Tomorrow?
Tomorrow night.
What is
the topic for tomorrow night? Mark, what's our topic for tomorrow night? Untangle, right? Untangle. Right. It's a... Untangle tries to be all things to all people with respect to DNH and DHCP and DNS and things like that, and tries to be a network appliance. Should be fun to watch. Right.